of a function of 2 variables, and then we will look at the gradient of a function of 3 variables. The gradient of a function is no more than its partial derivatives written in the form of a vector. So we take the partial of f with respect to x times I, and then plus the partial of f with respect to y times j, and that gives us the so-called gradient. The gradient is said to be tangent to the curve at the point that you examine, and so this is one very neat and quick way to examine the tangent vector. Back in chapter 12, we spent a lot of algebraic manipulation trying to calculate the unit principal tangent. But here's a very quick and neat way of getting to that idea. With the gradient, you can find the directional derivative as being the dot product of the gradient with the unit vector. There are some other neat properties of the gradient that if you take the gradient, it is said to be the direction of maximum increase. So if you're going up a slope, the most rapid increase slope would be the gradient. And if you negate it, then we get the direction of the most minimum increase of f. Is said to be the negative gradient. The maximum value of the directional derivative is said to be its norm, and then the minimum value of the directional derivative is the negation of the norm of the gradient function. The calculation of the directional derivative in the gradient for the 3 variable space is still the same argument, just highlighted and expanded to 3 variable system. Well, find the gradient of the function at the given point. So here the gradient of f at x comma y is 3 times I plus 10y times j, and to calculate the gradient at the point 2 comma 1 is 3i plus 10 times 1 for y. That's just 10j. Well, there's nothing to that. Now let's find the directional derivative by using the gradient. So the gradient here of f is 2xi plus 2yj plus 2zk. So we can use that, and now notice that this gradient at the point P, so x is 1, y is 1, z is 1. It gives us 2i plus 2j plus 2k. Now if you check v is the square root of 3 over 3i minus the square root of 3 over 3j plus the square root of 3 over 3k. Let's check his norm. Well, if you know that is 1, and it is, you can skip this spot. So here we take each term and square it under the radical. So that gives us the square root of 3 over 3 squared plus the negative square root of 3 over 3 squared plus the square root of 3 over 3 squared. Just don't like it. look at that. We get the square root of, this is 1/3 plus 1/3 plus 1/3. Gives us 1. So V is the unit vector. So that's good. So the directional derivative of the function f in the direction of u at the point 1, 1, 1 is said to be the gradient of f at the point 1, 1, 1. It's dot product with u. So this becomes the 2 times the square root of 3 over 3 plus 2 times the negative square root of 3 over 3 plus 2 times the square root of 3 over 3, which just gives us 2/3 times the square root of 3. So that's all that was involved there. What about this one? It says find the gradient of the function and then the maximum value of the directional derivative at the given point. The maximum value of the directional derivative is the norm of the gradient. So here you find the gradient of f. Well, we need to find those partial derivatives. If you know what this is, and we've kind of been working problems like this before, this is x over this square root. Well, if you need to see it for the first one, this is 1/2 times x squared plus y squared plus z squared to the negative 1/2 times 2x. So this is x over the square root of x squared plus y squared plus z squared. So the gradient of f is equal to, is x, let me write it like this. This is 1 over the square root of x squared plus y squared plus z squared times xi plus yj plus zk, instead of having to write that radical 3 times. Now you can plug that in. It says at the given point where x is 1, y is 4, and z is 2. So the gradient of f at the point 1, 4, 2. So that's 1 over the square root of, let's see, 1 plus 16 plus 4. So that's the square root of 21. And then this is I plus 4j plus 2k. Now it says find the maximum value of the directional derivative. So the maximum value of this directional derivative is the norm of the gradient. So this norm of the gradient is the square root of x squared plus y squared plus z squared divided by the square root of x squared plus y squared plus z squared. And this gradient is a unit vector, so we get 1. So here we have the square root of x squared plus y squared plus z squared divided by the square root of x squared plus y squared plus z squared. We get 1. Now it doesn't happen for all of the norms of the gradient, just for this one because the gradient came out to be a unit vector. This just so happens. to be a unit vector, just based on how it's defined. Here, find a normal vector to the level curve. Just note that the gradient of f at a point xy is a vector that is said to be normal to the level curve. The level curve here is f of xy equal to c. It becomes a level curve where that is, it becomes just a fixed value because the function f of xy is assigned to a number c. Well, look how powerful the gradient is, because the gradient doesn't even take into consideration c. So for 47, the gradient is negative 2i minus 3j, and it says at the point 0, 0, but here the gradient is just a plane, just a point, so it has no bearing. It's going to be this same value, so it's still negative 2i minus 3j. Now for 48, the gradient of f is equal to 2xi plus 2yj, and the gradient of f at the point 3, 4 is 2 times 3, which is 6i, plus 2 times 4, 8j. Well, that's all that we'll do for today. Thank you.